Okay. Recording, huh? All right. So the plan today, number one, we do pipe flow problem. Predict delta P given what? Given K prime and N prime. All right. Number two, power law fluid in pipe. Basically, relating K prime and N prime to K and N. All right. Pipe flow problem. All right. You predict delta P given K prime and prime. Power law fluid in pipe. So flow of all right. This one is a general fluid, huh? And number three, maybe we might look at a little bit of profiles. Velocity power law fluid and Bingham plastic. Okay? Right? So that's our plan today. Why so much furniture here? And then got big microphone today also. Hello? Huh? Karaoke night. Hello? Okay. Huh? Okay. Velocity profiles. Look at the pipe flow velocity profile. So, let's start. Okay, let's start with this problem here. No. All right. So, the standard I told you, we can measure the flow rate. All right. We can measure the pressure drop, and from that we can measure we can estimate the shear stress on the wall, and then how? All right. We can basically do a curve fit to find K prime and N prime based on that. All right. So normally the K prime and N prime come from the experimental measurement. This fluid is general fluid. We don't know what it is. Right? It could be power law fluid, it could be non-power law fluid. But for the instant that we do our measurement, or for the particular application, for particular instant in that particular flow condition, the K prime and prime is that. Alright? The K prime and prime may not be fixed also because the fluid is funny. If you double the flow rate, the K prime and prime might be a different value. Alright? It's general fluid. So here K prime and prime measured. Alright? For dimensional stability, dimensional compatibility, that's why the K prime has a value of Pascal second to the power N prime. Right? So that the shear stress equals to K prime, 8 U over di to the N prime. Alright? So this one they give you all the situation. Alright? So ask you to do this way. Okay? So K prime is 1.48, N prime is 0.3, velocity is 2, density is 961, diameter is 0.0762, length is 3.048. I don't know why the number is so funny. Okay? So predict pressure loss basically here. Neglecting N effects. Right? Neglecting minor losses are basically that one. Okay. Alright, you get that problem? You copy down the numbers? Alright. For bar school here also, yeah? Maybe at a forum here or something. Okay. Alright? Don't need to copy out every word, but just the values. Okay? So basically, as I said, alright, if you copy that. Okay? No, still go ahead. Don't copy every word, just copy the numbers now. Length, diameter, K prime, N prime, and so on. Okay? Alright, so we know, alright, shear stress on the wall equals to K prime 8U over DI to the N prime. Okay? We are able to measure this because, what is this? Delta P over L D over 4. Correct? Okay. Alright? Okay? So if we measure the pressure drop and we measure the flow rate, that's equal to Q over A, the average velocity and the pressure drop, we can get K prime and N prime, basically. Alright? And some of you might be tempted, let's see whether correct or not. Wow. So easy one. So what is K prime? 1.48. What is the velocity in the pipe? 2.0. What's the diameter of pipe? 0.07. Alright? 7 divided by N prime, 0.3. Alright? So what is this shear stress on the wall? What's the answer? And this is equal to, which is equal to delta P over, what's the length? 3.048. The diameter, 0.07 over 4. What is delta P? What's the answer here? 7.55. This will be Pascal, shear stress of force per unit area. Okay, delta P, and this will be correct if laminar flow is less than 2,200. Okay? What? 1169. 1177.69. Okay? Easy only, But then why you ask me all about RE prime and all that? Okay? This is correct if Reynolds number below 2,200. Let's check what the Reynolds number is and see whether it's still correct or not. RE prime is equal to rho V D over mu AP. Mu AP is equal to, what's mu AP? What mu AP is 8. Shear stress on the wall over 8U over DI. Is that correct? So it's actually K prime 8U over DI to the N prime over 8U over DI. Is that correct? Let me check before. No. Alright? No. Okay? New AP is K prime 8 UODI. Correct. Alright? So this one actually we already worked out here. K prime 8U over di to the n prime. This is 7.55. What is this value here? 8U over di. And that one is this one. Right? And then we put this value that we find in here. What's the density? 961. 961 velocity 0. 0. Velocity 2. 2 diameter 0.0762. Mu AP. What's the mu AP? What is 8U over di? Huh? 0.033. And therefore mu AP is what? Reynolds number is 4437.87. 0.033 is the mu AP, is it? Okay, so 0.033. You all okay so far? No issues? Huh? So 0.033. So this Reynolds number is already more than 2,200. So your luck no good this time. This one didn't work. Alright? So wrong. Okay. But wrong in this case. Not then go down this path. So we got Reynolds number is this one. So we need to find the F fanning. Okay? So that one we look up the graph. Remember our Reynolds number 4004 and our n prime 0.3. Don't know whether you can paste a copy. Copy here. Copy. Paste. Works. Okay. So 4,000, 1,000, 1,000, 2,000, 3,000, 4,000 about here. 4,000 how many? 4,005, 6, 7, 8. 4,004 is it? So about here. N prime 0.3. Okay, take here. 001, 002, 003, 004, 005, 6, 7, 8, 9, 10. 5 what? 5, 6 maybe? 0.0057. Alright? Okay? Is that okay how I already? Okay, logarithmic scale, R is prime. In this case, our n prime is 0.3, so we follow this 0.3 line. Never mind, dotted, it's extrapolated data, but never mind. Alright? Then you go there, it's 0.0057. Is that okay? Alright? So, and F fanning is defined as F fanning is a little bit more complicated. It's here. Go back here. F fanning is 0.0057 is equal to shear stress on the wall divided by half rho V squared. Alright, so shear stress on the wall is equal to 0.0057 times half rho V squared is equal to, what is it here? Delta P D over L over 4. So, you can put in the numbers. P equals to what? Pressure drop is how much? Pascal. Alright, diameter is 0.07. Length is 3.048. That came from the graph here. I don't need this graph right here, but it came from the graph here. Alright, Reynolds number and the F prime. Is that okay? So, this is the... So, if you want to learn one way to do it, alright, rather than two ways, You just follow this way. Don't go this path. Alright, this path only works in certain cases. You go down this path. This path works all the time. Laminar turbulent will always work all the time. Alright, you need to find a new AP. This is step 1. Step 2, find a Reynolds number. Step 3, you read up your graph. And step 4, you work out your shear stress on the wall, and then after that, the pressure drop. Okay, what's the delta P? Huh? 1,777.32, which is quite a lot bigger than this one, because this one assumes laminar flow. Okay. Alright, that's a typical question. Yeah. Okay. All right. The next step, I need to go to Moodle. Here, 2, 4, yes. Okay. Oh, they put the wrong set. Okay, so we do this problem. Alright? It's still a bit of the next week's tutorial and we do this problem. Alright? Power law equation, power law fluid governed by this relationship. Alright? If you know a particular fluid is power law fluid, alright, then it's governed by this relationship. Non-power law fluid. Alright? A general fluid which is measured in our what do you call it? In our pipe flow experiment, alright, has this relationship. How to relate the two? Okay, that's the problem. Right. Okay. This one I made copies. I given out yesterday for those who attended the tutorial yesterday. Those who attended the tutorial tomorrow, I'll give out this one because we are doing this problem set for this one. Alright, might as well do the answer. Okay, that's a little bit more updated. Okay. So, you all read the question? You all okay? Don't need to copy down. I'll give you a printout for this one. Okay? A power law fluid. Is that all right? Any questions? Yeah. All right. So basically, power law, shear stress is equal to K alpha dot to the N. Pipe flow, experiment, general fluid, shear stress is equal to K prime 8U over DI to the N prime. Alright, how they're related. First of all, remember yesterday, Tuesday, I talked about that funny long equation. Alright, basically that equation, alright, from the pipe flow experiment, we were able to determine, alright, alpha dot at the wall is equal to alpha dot wall comma Newtonian 3n plus 1 over 4n, right, n prime. Okay, this some funny name, Mooney equation or something. Okay, I told you, for those who love to think about it, by all means. Here. Okay. Here. All right, it starts here. Okay, it starts here by integrating flow rate. And then we convert the flow rate, the R, into shear stress, and then integrating shear stress from the center all the way to out at the wall, and then a bit more manipulation and so on. Okay, and you get to this one here. All right, this one is basically 1 over n prime. This is the shear stress at the wall for your pipe flow experiment, and this is the shear stress on the wall for a Newtonian fluid, that's AD over DI. Okay, so in summary, that is that's a summary. Okay, in summary, that this is it. In summary, okay. So normally you're not asked to prove it. Okay, that's proven here. That's the name, Rabonowitz-Mooney equation. Okay, so we just apply that. If you don't believe, then you have to prove this to yourself, by all means. I used to try to describe it, but normally nobody understands, so that's waste my time and yours. Okay, so where we go? Okay, so shear stress, we put this in here. All right, shear stress. This equation should apply at the wall. So this one's at the wall. Okay, should apply everywhere. So it should apply at the wall. All right, shear stress on the wall is equal to K. This one is actually this one. Shear stress on the wall, Newtonian, dot 3n prime plus 1 over 4n prime to the power n. Okay, so this one is equal to K. This value is 8u over di to the n. All right, and this value is 3n prime plus 1 over 4n prime to the n. Okay, first, so you compare this creature, compare these two creatures, right? Okay, they compare well. So basically, this must equal to this. So first of all, n is equal to n prime already. Right or not? 8u over di to the n, 8u over di to the n prime. They must equal to each other. So if n is 1, is therefore n equals to n prime, and that really governs whether it's a shear thinning, shear thickening, or Newtonian fluid. N is 1 Newtonian, n is less than 1 shear thinning, and more than 1 shear thickening. Right? We discussed earlier. And we can say, because why I draw in red, this one must be equal to this one. Okay, they must. No two ways about it. Right or not? And therefore, K prime, the other one, in green, K prime is equal to K 3n prime plus 1 over 4n prime. Here n and prime is the same, so up to you. I want to put n prime. Okay? So that one is general fluid. Okay? So the remaining, that K prime, must be equal to this, what's remaining here. So up to you, is n prime equals to n, it doesn't matter. you can also write k prime is equal to k 3n plus 1 over 4n to power n. I can drop the prime, it doesn't matter. It's the same. Alright? So if you know it's a power law fluid, okay, or k is equal to k prime 4n over 3n plus 1 to the n. Okay? If you know it's a power law fluid, okay, and you measure k prime and n prime, you can actually extrapolate what you can actually calculate what k and n is. Right? Is that okay? Any questions? So what I was saying is, if you do the pipe flow experiment and you measure k prime and n prime, and you also know for certain fact that it is a power law fluid, you can estimate the k and n through this way. Right? Because you measure k prime and n prime, you can measure the k and the n for power law fluid. Okay? But there's no way to know lah. But if you, let's say you're pretty certain that it's a power law fluid, all right, from a very reliable source told you, all right. Okay, then any questions? Sir? Well, left and right. Here, from here to here, from here to here. So this one and this one the same. So put this equation in here to get this one. Circle. I'm comparing the two. This one is from here. This shear stress on the wall for Newtonian fluids AU over DI. Is this from here to here? This one is basically the flow characteristics. We talked on Thursday or Tuesday that for Newtonian flow, all right, in a pipe, the velocity gradient at the wall is this one. Okay, which is this one. This one is basically the correction factor, and this one is basically the correction factor. This one is the AU over DI, the velocity gradient on the wall for Newtonian fluid, and this one is basically the velocity, the strain rate at the wall for the pipe flow experiment that you did. Okay, so basically when you measure the k prime and n prime and you did some of that analysis, you go round and round. Okay, you get this relationship. So with this relationship, you are able not only to measure k prime and n prime, you are also able to estimate analytically based on the measurements what of k prime and n prime, what the shear stress on the wall is for a pipe flow experiment. Right? From your experimental data. Okay? Is that alright so far? Okay. Okay. And then this one I also sometimes do, but I think maybe I just show it to you and ask you to look at it. Sunway. Okay. Don't have. Oh, yeah. No, I haven't put it up here. Never mind lah. Okay. All right. Actually, I've solved it a separate piece of paper and I'll upload it on Moodle if you want to look at it. This one is deriving the velocity profile in a pipe for a power law fluid. Alright? So it looks like this. Okay. Number one, there's a correction factor here. Alright. And number two, there's also the power is no longer just parabolic. The power here depends also on n. Alright? So if n goes to 1, let's find here parabolic. If n gets very small, then it becomes like straight lines. If n very big, then it becomes like a very high order polynomial. Let's see the shape. Huh? Okay? So if n approaches 0, right? N approaches n increases. Let's see right. N approaches infinity. Alright, then this over this approaches 1. Alright, then it becomes like a straight line. Okay. For n very large, it becomes a straight line. For n very small, it becomes basically like a uniform flow. N very small. Alright, this approaches 0. 1 over 0. No. Yeah. So this approaches, this becomes very big. And therefore this whole thing, because this is a fraction, becomes very small, it becomes like a straight line. Alright, so Newtonian flow you expect parabolic, where n large, you get a straight line, thickening, and when I shear thinning, you get a straight line. So you get a velocity profile somewhere in between. I'm sorry I haven't put it up yet. I'll put up on the Moodle this one. How I go from here to here. I'll put up my handwritten notes. I thought I did but Moodle sometimes you have to hit the submit button on. So when you're uploading and you go off and do something else, you don't hit the submit button. Although you finish uploading, but it doesn't actually commit it. Some issue there, I don't know. Okay, final one. Bingham plastic. Okay. So again, you can work out the velocity profile. All right. Play around with it. Okay. But it's important to note with Bingham plastic, basically there's one section because the shear stress approaches 0 at the center line. Right or not? The shear stress is highest at the wall and 0 at the center line. So when the shear stress drops below the yield limit, it behaves like a solid. And here it behaves like a fluid. So with this type of flow profile, you get a uniform flow called a plug flow in the middle, which is basically like a solid plug and a solid train moving at a constant speed. Alright? And then here's where the shear stress is high, and you get the parabolic profile. Alright? So that, and the deviation of the velocity profile also I think is, I didn't put here, but that's the final outcome. Okay? Velocity of the plug is this one, and velocity of the profile outside the plug is this one, depending on your R and your pressure that's driving the flow. Okay? Finally, I'll mention this one. If you need to find the pressure drop in a Bingham plastic, then you're supposed to use this equation. But I didn't see any question in our tutorial this year. So I'm not sure whether I need to do it. Alright? So basically, you have an equation that has your fanning friction factor. First, you calculate your Reynolds number, all right, and then you calculate your, what number is this called? Storm number. All right, this is a non-dimensional parameter which includes your yield stress and your Bingham viscosity. All right, you calculate these two numbers. You put in here this equation. All right, this for experimental. Based on experimental results, they come up with this equation for Bingham plastic. Alright, find your F. And then after that, from your F, this is your fanning friction factor. You can find the shear stress on the wall and then your pressure drop and so forth. Alright, the only problem with this one is there's an F here. But you're finding F. So how do you do that? Right now, you're very good at guessing anything. Right? So you have to guess the F. And see whether the F you guess correct or not. Alright? If not correct, then you have to guess again. Alright? Okay, so that's once you got finding friction factor, finding the pressure drop is same as in the okay? This for laminar flow. Okay, are there any questions? Okay, I essentially finished what I have to say. You want to do 1 to 12, some more tutorial also, yeah, let's do next week. Right? Go home early, after jam already outside. Alright. Okay, which one you want to do? 1, 2, or 3? Yeah? No, this question 3 is ABCD one. What's this? Alright, let's do question 2. Alright. Should be done in about 20 minutes. So we don't you try to draw in 15. It depends how fast you guys work. Alright, so pumping characteristic of brand of Australian honey 1490 was started pumping honey through a pipe, diameter 25.4 and length to diameter ratio of 160. Alright, the pressure loss measured at 3 different flow rates given as. Okay, so let's do question 2. Alright. Hey, I don't know this one. Okay. So 1490 diameter 25.4. L on D is 160. .6. K prime is 7.6 and prime is 0.96. All right, so it's not very easy. Okay, based on that one, calculate for each of these. Maybe I save a copy first. All right. Fine. Okay, so what we need to do is for each value, we want shear stress on the wall is equal to K prime 8u over di to the n prime. Alright, so for each case, we can calculate the shear stress on the wall. Shear stress on the wall is equal to, what's it? What is it? Delta P L. Alright, so this one very easy. They can L over D 160 already. So it's delta P over 160 times 4. Correct or not? Alright, so for each one, calculate the number here, here, and here. On this side, we need flow rate, kilograms per hour. We need to find the velocity U. Alright, rho A V m dot is equal to rho AV. We want V. V is equal to m dot over rho A, which is equal to m dot given. Alright, m dot. Rho is what? 1490. Area is pi 25.4 over 1000. Okay. M dot here is kilogram per hour. So we need to get kilograms per second. So we need this one, m divided by 60 square. Okay, so you find the u for each value. And then after that, you find, here you find k prime 8u over di to the n prime. Alright. And if this value agree with this value, then we are good. If not, then it's not good. Okay? So basically, this one, I'm finding the shear stress on wall based on pressure drop. Here, I'm finding the shear stress on the wall based on the relationship K prime, KU, di, N prime. Alright? If they match, means the estimate value for K prime, N prime is good. If they don't match, means the estimate value for K prime, N prime is not good. Does that make sense? Huh? Shear stress on the wall can be measured and can be predicted using K prime and N prime. That one is measured, this one is predicted using K prime and N prime. Alright? If the measured match the predicted using K prime and N prime, that's good value for K prime and N prime. Alright? And also for this particular fluid, the K prime and N prime is quite constant. Is that all they asked for? So small. I think so. Newtonian or non-Newtonian? Let's see. N prime is 0.96, very close, huh? Very close to 1. So maybe Newtonian. Right? It's very close, huh? 0.96 and 1. Your experimental error 5% already gone already. Alright? So, you got answers or not? Anybody calculating? Calculator too small. Also, the other thing that we need to make sure is the flow lamina. So, to calculate that one, just take the highest value. Take at m equals to 354 kilograms per hour. Alright. What is the u? Equals, what is the mu AP is equal to 8u over di. Okay. K prime 8u over di to the n prime minus 1. Re prime is rho u di over mu AP. Okay, that's my final check. But before we do that, what's the answer here? Anyone calculating? 60 divided by 160 by 4. Oh, 60,000, huh? Okay. Huh? 30? 93.75. Second one? 187.1. Third one? Huh? 5. Fourth one? Sorry, third one? 281.25. Alright, all these are in Pascal. On this side, what's the U? M dot divided by 60 squared divided by 1490 divided by pi divided by 25.4 times 1000. Hey, there should be a square here. Pi d squared. Hey, over 4. Okay, confusing. 1490 times pi d is 0.0254 squared over 4. Pi d squared over 4. What's the answer? Let other people do. Yeah. Other people, what is the answer? What's the answer? M, what's M? Huh? U mean? Yeah, M is 118,236,354. Try all three. Which one? First one. 156 meters per second. Can't be lah, that's why. First one is 0.043. Okay. 156. Normally, Newtonian flow, very viscous one. Cannot, reach 1 meter per second also very difficult. Yeah. Alright, cannot reach 100 meters per second. It's near impossible. Alright. What's the others? 236? What's the second one? 0.0? 87. Third one? 0.130. Four three eight seven one three oh. Okay, what's the this one based on if you put this inside here? K prime here is what? K prime is 7.6, N prime 0.96. Calculate the shear. Within 5% or not? Okay. Answer? 0.0? What's the first one? It should be around 93.75 lah. But I don't think it's exactly there. 92.75. Oh, very close. This one? Huh? DI 25.4 mm. 160. The length to diameter ratio. Yeah, what is it? What's the answer? Second one? 182.4. Third one? 286.7. Very small, less than 5% difference. Less than 5 Pascal difference. Okay, it's good experiment. Right? Okay? Good. Okay? And finally, here is U is 0.130. Alright? Just to check, make sure that all the flow, I believe it is velocity so low. Alright? But just to check that the mu AP, that it is laminar, let's just calculate the RE prime for the highest flow rate. Alright now, if the highest flow rate is laminar, you expect the lower flow rate to be laminar? Yes, right. So don't need to check all three. Okay, just check the highest one. So at 354 kg per hour, the velocity is 0.130. Calculate mu AP and RE prime, and then after that, if you get the answer, we can go on. Alright, I expect to be less than 2,200. So, laminar. Okay? Safe. Huh? Mu AP. Huh? What's the answer? Huh? A times U. U. What's the answer? But this one very small, 0.04. Power 0. Yeah. Nearly to power 0. So you get somewhere very close to 7.6. 6.55. Okay. Alright. So rho is 9. No, 9. 1. 1490. 1490. 0.130. 0.75. What's 0.75? You calculated already. Okay, 0. This value here is 0.0254 divided by mu AP is 6.55. And your answer is 0.75. So, okay, definitely laminar. Alright, that's fine then. Safe. Okay, that's it. Okay, final discussion. For ChemEng students, some say got test next Monday, and then they want to do it. They want to do the multi-phase flow part the following Saturday. Some say no, I'm okay. I can do the test and I can attend the thing. So, what's the general consensus? Huh? Yeah. Who give you test or research? You know? Huh? Who? The lecturer. Huh? The job. You guys. Hmm? At least the student's not lecture name. Quite worrying, science student. What's your lecture name? Don't know. Okay, so what's the consensus? Prefer this Saturday or next Saturday? Next Saturday. So week 12 Saturday. I think I booked a room already. I think it's in 600. They didn't want to give me this room, so they give me some other room. I think it's 6007 or something like that, or 608. One of the lecture theatres here. I'll send out email. Okay. Alright. See you next week or tomorrow in the tutorial.